I want to make the most unfashionable claim in all of popular science. Not unfashionable in the sense of being obscure or overlooked, unfashionable in the sense of being something that almost no one working in science communication, space advocacy, or public-facing physics will say out loud, because it contradicts one of the most deeply held narratives in modern culture. The idea that humanity is destined to spread from Earth to the stars. The claim is this: humanity will almost certainly never leave the solar system, not in the next century, not in the next millennium, not as a biological species traveling in spacecraft. The physics does not permit it on any timescale relevant to human civilization, and the conditions we would encounter if we somehow made the journey would be incompatible with survival in any form we recognize as human. I want to be precise about what I mean, because imprecision is what allows the optimistic narrative to persist. I am not saying that no physical object will ever leave the solar system. Voyager 1 and Voyager 2 have already done that. I'm not saying that we will never send small robotic probes to nearby stars. The breakthrough starshot concept, as I described in the interstellar travel video, proposes to accelerate gram-scale probes to 20% of the speed of light using a laser array. Whether that specific proposal is achievable is unclear, but the physics does not forbid it. What I am saying is that the transport of living human beings from the solar system to another stellar system with any plausible technology derivable from known physics is not achievable on the timescales of human civilization, possibly not on any timescale, and that the honest confrontation with this fact should change how we think about the future of our species and our responsibilities on this planet. Let me build the argument layer by layer, because each layer is separately sufficient to establish the conclusion, and together they form a case that I believe is unanswerable with any technology based on known physics. The first layer is energy. I described this in detail in the interstellar travel video, but let me restate the core numbers, because they are so extreme that repetition is warranted. To accelerate a spacecraft of 1,000 tons, a conservative minimum for a life support capable crewed vessel, to 10% of the speed of light requires approximately 4.5 times 10 to the 21st joules. This is 10 times the total annual energy production of all human civilization on Earth. Every solar panel, every nuclear reactor, every coal plant and gas turbine on the entire planet running for a full year produces 10 times less energy than the kinetic energy of this single spacecraft moving at 10% of C. To reach 20% of C, the energy requirement is roughly 4 times higher. To reach 50% of C, approximately 60 times the annual global energy production. These numbers assume perfect conversion of energy to kinetic energy with zero waste. Real propulsion systems are not perfectly efficient. Chemical rockets are approximately 0.0000001% efficient at converting fuel mass to kinetic energy of payload. Even nuclear propulsion systems, the most energetically credible technology we can envision, would require mass ratios of propellant to payload that make any crewed interstellar mission impractical. The Tsiolkovsky rocket equation is the fundamental barrier for a rocket that carries its own propellant. The mass ratio equals e to the delta v divided by exhaust velocity. For any exhaust velocity achievable with known physics, and any delta v appropriate for interstellar travel, this ratio is astronomical. A nuclear pulse drive with an exhaust velocity of 1,000 kilometers per second would require a mass ratio of approximately e to the 30 to reach 10% of C, which is 10 to the 13 kilograms of propellant for every kilogram of payload. For a 1,000-ton spacecraft, that is 10 billion tons of nuclear bombs that must be carried from Earth. The only escape from the rocket equation is an external energy source. Laser sail propulsion, solar sails, and similar concepts avoid carrying propellant. But these require power infrastructure of extraordinary scale at the source, and the coupling efficiency between beam and sail drops precipitously over interstellar distances. Scaling these concepts from gram-scale probes to human-scale spacecraft is not a matter of engineering detail. It is a matter of energy physics that currently has no solution. The second layer is time. Even granting the impossible energy, the journey takes decades to centuries at any velocity achievable with any technology we can currently imagine. At 10% of c, the journey to Proxima Centauri takes 42 years one way. The crew ages for 42 years in transit, while Earth ages for the same 42 years. A round trip takes 84 years of crew time. This is a single human lifetime entirely consumed by the transit. At higher velocities, relativistic time dilation begins to help the crew. At 90% of c, the one-way journey takes 4.7 years of solar system time, but 2 years of crew time. At 99.9% of c, 4.3 years solar system time and 0.2 years crew time. But reaching 99.9% of c requires energy that exceeds the total mass energy of the known universe, converted with perfect efficiency. It is not an engineering challenge. It is a physical impossibility. For any mission at velocities achievable with technology based on known physics, the mission duration is decades to centuries. This creates a set of problems that are individually insurmountable and collectively decisive. The crew must survive in an isolated environment for decades, with no possibility of resupply, repair by outside specialists, or emergency evacuation. The psychological and social challenges of this have no parallel in human history. The longest isolated human missions on record, the Concordia Antarctic Winter Over Program and the Mars 500 isolation study, are months long, not decades. The extrapolation from months to decades is not supported by any data and is almost certainly unfavorable. The mission must be funded, maintained in purpose, and supported by an institutional infrastructure on Earth for the entire duration. Human institutions do not maintain consistent focus on a single objective across 40-year time frames. Programs are defunded, priorities change, wars occur, civilizational disruptions happen. The Apollo program was 12 years from inception to the last lunar landing and was then canceled. 40 years of continuous, uninterrupted, institutional commitment to a crewed interstellar mission has no historical precedent in human civilization. If this is already shifting how you think about humanity's trajectory, the principles I have collected about what the universe allows and what it does not are directly relevant here, ready to change how you see the world. Get your copy of 12 Principles for Understanding the Fabric of Reality at realityprinciples.com. The third layer is biological. Human beings evolved on Earth over approximately 4 million years of hominid evolution and several billion years of prior biological evolution. Every aspect of our physiology reflects this specific evolutionary history. Our bone density, our immune system, our cardiovascular system, our neurology, our psychology, our microbiome. We are extraordinarily well adapted to one specific environment. The surface of Earth at approximately 1 atmosphere of pressure, with a specific atmospheric composition, a specific temperature range, a specific radiation environment, and a specific gravitational acceleration. Space is hostile to this physiology in ways that technology can partially address and in ways that it fundamentally cannot. In microgravity, bone and muscle loss are progressive and severe. After 6 months on the International Space Station, Astronauts typically lose 10 to 15% of bone mineral density in the lower extremities and significant muscle mass despite 2 hours of daily exercise using resistance devices specifically designed to mitigate this loss. After 1 year in microgravity, some astronauts show bone density reductions of 20% or more in the most vulnerable regions, the spine and the hips. Fracture risk increases proportionally. The mechanism is straightforward. Bone is a living tissue that responds to mechanical loading. When the skeleton does not bear weight against gravity, the bone remodeling cycle shifts toward net bone resorption. Osteoclasts, which break down bone, outpace osteoblasts, which build it. The skeleton adapts to the reduced loading by becoming thinner and less dense. This is not a disease that can be cured with drugs. It is a physiological adaptation to the actual mechanical environment. In zero gravity for years, the skeleton would degrade to levels inconsistent with normal physical function. Artificial gravity through rotation is the mitigation, but it requires a habitat rotating at 2 revolutions per minute with a radius of approximately 225 meters to produce 1 Earth gravity without causing debilitating motion sickness from the Coriolis effect. Such a structure adds enormous mass and engineering complexity to any spacecraft design and would need to be spin up and maintained for the entire 40-year transit. The cardiovascular system also degrades in microgravity. The heart, adapted to pumping blood against the column of blood pressure created by standing upright in Earth's gravity, partially atrophies when this loading is absent. Cardiac muscle mass decreases, cardiovascular output decreases, the risk of orthostatic intolerance, the inability to maintain blood pressure when standing increases. After long periods in microgravity, astronauts returning to Earth have required careful rehabilitation to regain cardiovascular function. The radiation environment in interstellar space is a separate and severe problem. Galactic cosmic rays, high-energy charged particles from supernovae and other galactic events continuously bombard any spacecraft in interplanetary or interstellar space. The Earth's magnetic field and the heliosphere provide partial shielding in the inner solar system. Outside the heliosphere, the full, undepleted cosmic ray flux is present. The biological effects of galactic cosmic rays have been studied extensively in animal models. Mice exposed to doses equivalent to a one-way trip to Mars show measurable cognitive impairment, including deficits in memory, consolidation, spatial learning, and executive function. The mechanism involves direct ionization of neurons and support cells, inflammatory cascades in the central nervous system, and disruption of the synaptic plasticity that underlies memory formation. For a 40-year transit to Proxima Centauri, the cumulative cosmic ray dose would be roughly 80 times the annual exposure at the ISS, which is already above the lifetime limits for radiation workers on Earth. The cognitive effects accumulated over this dose are unknown in humans, but are expected from the animal studies to be significant. A crew that arrives at Proxima Centauri after 40 years of cosmic ray exposure may not be cognitively capable of performing the complex tasks that arrival in a new stellar system would require. The psychological challenges are equally severe. 40 years in a closed environment with a fixed social group, no possibility of escape or rescue, communication delay of years with Earth, and the knowledge that return is a lifetime away creates a psychological burden for which there is no historical analog and no demonstrated human capacity. The longest isolated confinement studies include the Antarctic Winter Over programs, which isolate small groups for approximately 8 months in extremely harsh conditions. These studies document significant rates of depression, interpersonal conflict, cognitive impairment, and reduced performance during the 3rd and 4th months of isolation, a phenomenon called the third quarter phenomenon. The extrapolation from 8 months to 40 years is not a matter of scaling. The psychological effects may not simply increase linearly with duration. They may compound in ways that make decades-long isolation qualitatively different from months-long isolation in ways that cannot be predicted from the available data. The fourth layer is destination. Even if the crew survives the journey and arrives at the nearest star system, what do they find? I described in the Proxima Centauri b video the specific and severe problems with the only confirmed planet in the habitable zone of Proxima Centauri. It is almost certainly tidally locked. Its star produces flares of UV radiation multiple times per day that are hundreds to thousands of times more intense than the most extreme solar flares. Its magnetic field is uncertain. Its atmosphere, if it has one, is probably being stripped by the stellar wind. The TRAPPIST, one system, the next most studied collection of potentially habitable planets, is 40 light-years away, around another red dwarf with the same fundamental problems. The nearest solar-type star with confirmed Earth-like planets in its habitable zone is an unknown distance away, likely tens to hundreds of light-years. There is no confirmed destination within any plausible range of crewed interstellar travel that offers conditions hospitable to unprotected humans. Every identified candidate has severe problems. Every planet around a red dwarf, which constitutes 75% of all stars, faces the radiation and tidal locking problems I described. Every planet around a solar-type star within 10 light-years has not been confirmed to have an Earth-like atmosphere, magnetic field, or surface conditions. The fifth layer, and the one that I think is most underappreciated, is evolution. Human beings are not a fixed biological type. We are an evolving species at a specific moment in evolutionary time. Over thousands of generations, in an isolated interstellar environment, a founding population of a few thousand people would diverge genetically from the terrestrial human population. The specific selection pressures of the spacecraft environment, reduced gravity, elevated radiation, closed ecosystem, extreme social confinement, would drive evolution in directions that cannot be predicted from our current phenotype. After dozens of generations in the spacecraft, the population would not be biologically identical to the humans who departed. After hundreds of generations, they might not be recognizably human by any meaningful biological criterion. The species that arrived at the destination star system would be a different species from the one that left Earth. Whether this matters depends on what you consider important about the project of human civilization expanding into the galaxy. If the goal is to spread life, any diverged population of hominids would qualify. If the goal is to preserve human culture, knowledge, and identity, the scenario is less satisfactory. A population that has been isolated and evolving for centuries would have a different culture, different values, different knowledge base, and potentially different cognitive architecture from the Earth population. The realization that humanity is shaped by and embedded in a specific physical environment, that we are not a universal species who can simply relocate to any habitable world, is one of the deepest insights in both biology and physics. This kind of thinking about the constraints that define what we are and what we can become is central to my book. Get 12 Principles for Understanding the Fabric of Reality at realityprinciples.com. Let me now address the objections, because there are several serious ones that deserve precise responses. The first objection is that technology will advance, future propulsion systems, fusion drives, antimatter drives, or something entirely new will make interstellar travel possible in ways that current physics does not allow. The response to this objection has two parts. First, there is a clear distinction between technology that is unknown but physically possible and technology that violates the laws of physics as we understand them. Fusion propulsion is physically possible. We know fusion works. It powers the sun and has been demonstrated in hydrogen bombs. The challenge is containing and directing a fusion reaction to produce net positive thrust in a compact device. The specific impulse of a fusion drive is estimated at approximately 1 million seconds, corresponding to exhaust velocities of approximately 10,000 kilometers per second. This is a factor of 1,000 better than nuclear thermal propulsion and would dramatically reduce the mass ratios required for interstellar travel. But even fusion propulsion does not solve the interstellar problem. At exhaust velocities of 10,000 kilometers per second, the mass ratio required to reach 10% of C with a crewed spacecraft is approximately e to the 3, or about 20. This is aggressive, but physically tractable. You need roughly 20 kilograms of propellant for every kilogram of payload. The problem is producing the fusion fuel in sufficient quantities. The most energetically favorable fusion reaction, deuterium, helium-3, requires helium-3, which is rare on Earth and must be mined from the lunar surface or the atmospheres of the giant planets. The quantities required for an interstellar mission are astronomical by any realistic mining operation. Antimatter propulsion is the theoretical maximum. Matter-antimatter annihilation releases energy equivalent to E equals mc squared for the combined mass, which is the highest energy density permitted by known physics. An antimatter drive could achieve exhaust velocities approaching the speed of light, making interstellar travel at a significant fraction of c physically tractable in terms of mass ratios. A spacecraft using antimatter annihilation as propellant and reaching 50% of c would require a mass ratio of only about 3, meaning 3 times the spacecraft mass in antimatter fuel. But there's one insurmountable practical problem: producing and storing antimatter. The current global production rate of antihydrogen at all particle physics laboratories combined is approximately 15 nanograms per year. The energy required to produce 1 gram of antihydrogen using the most efficient known process is approximately 25 petajoules, roughly the energy output of a 1 gigawatt power plant for 8 centuries. To produce enough antimatter for a crewed interstellar mission at moderate velocity would require a dedicated antimatter factory running for centuries, powered by energy equivalent to the entire current global energy infrastructure. Whether future technology could dramatically improve antimatter production efficiency is unknown. The theoretical minimum energy to produce an antiproton is 938 MeV, set by the rest mass of the antiproton. Current processes are roughly 1 billion times less efficient than this theoretical minimum, meaning there is in principle a factor of 1 billion improvement possible. Whether any physical process can approach the theoretical minimum while producing macroscopic quantities of antimatter is unknown. The second part of the response to the technology objection is that we should judge the probability of the relevant technology existing based on the evidence we have. We have been developing propulsion technology for a century. In a century of development, we have almost reached the physical limit of chemical propulsion. Nuclear propulsion, developed in the 1960s and never deployed in space, offers a factor of 2 improvement. Fusion and antimatter propulsion, which would offer factors of thousands to millions of improvement, have not been demonstrated at any scale relevant to propulsion and face fundamental physics challenges in their production and storage. The second objection is that AI, or uploaded human consciousness, could make the journey in robotic form, avoiding the biological constraints. This objection conflates the question of whether humanity will leave the solar system with the question of whether any human-derived intelligence will. An AI system is not humanity. An uploaded consciousness, if such a thing is even coherent as a concept, raises deep philosophical questions about personal identity and continuity that are not resolved by the physics. Whether an information pattern instantiated in a different substrate in a computer rather than a biological brain is the same person is not a physics question. It is a philosophical question with no scientific consensus. The claim I am making is specific. biological Homo sapiens will not make the journey between stars on any timescale relevant to our civilization. If we redefine humanity to include any intelligence derived from human origins, the argument becomes different and potentially more favorable to optimism. But that is a different claim about a different kind of future, and it sidesteps rather than addresses the question of biological human expansion into the galaxy. The third objection is generation ships, vessels large enough to sustain multiple generations of humans throughout a multi-century journey. Generation ships face all the energy and radiation problems I described. They also introduce additional problems. They require a self-sustaining ecosystem for centuries. The longest closed system habitat experiment, the Biosphere 2 project in Arizona, failed to maintain a breathable atmosphere and required external intervention after 2 years. Oxygen levels fell from 21% to 14%, equivalent to the air on a mountain at 4,000 meters altitude, within months. The failure was caused by unexpected interactions between the concrete of the habitat, soil microorganisms, and the atmospheric chemistry. Scaling from 2 years to 2 centuries with a reliably self-sustaining ecosystem is not a matter of engineering refinement. It requires solving closed ecosystem dynamics that remain beyond our current understanding. The fourth objection is that the timeline for interstellar travel is very long, and we should not project our current limitations onto a civilization that might exist 10,000 or 100,000 years from now. This objection is the most powerful and the hardest to refute directly, but it has limits. The laws of physics as we know them are not going to change. Within the physics we know, certain things are impossible regardless of the level of technology. And within the physics we know, the energy required for crewed interstellar travel at any velocity that makes the mission practical is orders of magnitude beyond any technology we can envision. Future physics might change this. But betting humanity's long-term strategy on physics that does not exist and that might not exist is not a responsible intellectual position. The honest conclusion is that within any physics that we can currently conceive as being a natural extension of what we know, crewed interstellar travel is effectively impossible. Future physics might change this, but we should not plan as if it will. The distinction between what might be possible in a world with unknown physics and what is possible given what we actually know is one of the most important intellectual habits you can develop. It is one of the 12 principles I explore in my book. Ready to change how you see the world? Get 12 principles for understanding the fabric of reality at realityprinciples.com. Let me now address what I think is the most important implication of the argument I have made. If humanity will never leave the solar system, what does that mean for the long-term future of our species? The standard answer to this question in science fiction and in the optimistic strand of futurism that runs through popular science is catastrophic. It means we are a dead-end species confined to a single solar system that will eventually become uninhabitable when the sun expands into a red giant in approximately 5 billion years, and that we will eventually be extinguished along with the sunday. I think this framing, while logical, misses what is actually important about the constraint. The Earth will remain habitable for hundreds of millions of years. The sun will not begin its red giant expansion for approximately 5 billion years. The specific problems that threaten human civilization in the near term, climate change, biodiversity collapse, resource depletion, political instability, pandemic disease, are all terrestrial problems that occur on timescales of decades to centuries. The interstellar travel problem is a problem on timescales of billions of years. If we are genuinely concerned about the long-term survival of our species, the relevant constraint is not the inability to reach other stars. It is the fragility of the conditions on Earth that we are actively degrading in real time. The specific list of what threatens humanity on a century timescale does not include the inaccessibility of Proxima Centauri. It includes the disruption of the climate system, the collapse of ecosystems that provide food, the depletion of aquifers, the acidification of oceans, and the breakdown of the social and political systems that allow complex civilizations to function. The narrative that humanity's destiny is to spread to the stars has a specific and harmful effect on this situation. It creates the impression that Earth is temporary, a launch pad rather than a home, and that the problems of this planet can ultimately be escaped by moving on to the next one. This impression is physically wrong. Earth is not temporary for any timescale relevant to our civilization. And the idea that we can escape to the stars is not just physically impossible, it is morally hazardous because it relieves the psychological pressure to solve the problems we face here. The physics of interstellar travel does not say that our civilization has no future. It says that our civilization's future is here, in this solar system, on this planet, for the foreseeable future and possibly forever. The extraordinary accident of conditions that makes Earth habitable, the specific properties of the sun and the moon and the magnetic field and the atmosphere and the oceans and the biosphere, is not going to be replicated at another star on any time scale we need to plan for. There is another argument that deserves mention, which is the possibility of expanding within the solar system rather than leaving it. Mars, the moons of Jupiter and Saturn, and the asteroid belt contain resources and, in some cases, conditions that are more hospitable than any environment outside the solar system. Mars at its worst is better than interstellar space. Europa's subsurface ocean is more interesting than the interstellar medium. The asteroid belt contains more concentrated mineral resources than any target we could reach outside the solar system. An expansion within the solar system is physically achievable in principle. The energy requirements are orders of magnitude smaller than for interstellar travel. The timescales are decades rather than centuries. The radiation environments are manageable with known shielding technology. Mars is 1.5 astronomical units from the Sun. Europa is 5.2 astronomical units. Titan is 9.5 astronomical units. These are nearby compared to the nearest star at 268,000 astronomical units. Whether humanity will successfully expand within the solar system is a separate question from whether we can reach another star. The former depends on political will, economic resources, and technological development that are difficult to predict. The latter is constrained by physics in ways that are more fundamental. The physics of interstellar travel does not say that our civilization has no future. It says that our civilization's future is here in this solar system. And the solar system is vast. Mars, the moons of Jupiter and Saturn, and the asteroid belt contain resources and, in some cases, conditions that are more hospitable than any environment outside the solar system. Mars at its worst is a far better destination than Proxima Centauri b. A round trip to Mars takes approximately 900 days, not 40 years. The energy requirement is orders of magnitude less than for an interstellar mission. Europa's subsurface ocean may harbor microbial life. Titan has a thick nitrogen atmosphere and complex organic chemistry. A single metallic asteroid, a kilometer in diameter, contains more iron and nickel than all of human civilization has ever mined. An expansion within the solar system is physically achievable. Not easy, not cheap, but not forbidden by the laws of physics in the way that interstellar travel is. Whether humanity will successfully do this depends on political will, economic resources, and technological development. But the physics does not preclude it. Let me close with what I think is the correct emotional and philosophical response to the conclusion that we will never leave the solar system. The response is not despair. It is not nihilism. The constraint does not mean our civilization is without meaning or without future. It means our civilization's meaning and future are here, in this specific system, on this specific planet, in this specific biological form, the sun will continue to provide energy for hundreds of millions of years. The Earth's biosphere has been evolving for 3.8 billion years and contains more complexity, more information, more beauty than anything we know of in the observable universe. Human civilization, with all its imperfections and all its violence and all its extraordinary creativity, is the most complex known phenomenon in the cosmos. All of this exists here. None of it requires access to another star system to be significant. The constraint of being bound to the solar system is not a limitation on what matters. It is a clarification of where we need to direct our attention. The universe is vast and largely inaccessible. The solar system is our domain, the only domain we will ever have, and it is extraordinary. The physics of interstellar travel tells us to look inward, not outward, for the future of the species. Not because the stars are not real or not interesting, but because they are not reachable. And because here, in the solar system, in this fragile and irreplaceable corner of the universe, is everything we have ever known and everything we are ever likely to have. The argument we have been making is, at its core, an argument about what it means to be bound to a specific place by the laws of physics, and what that says about where meaning and responsibility actually lie. That kind of thinking, grounded in the actual structure of the physical world, is what the 12 principles in my book are built on. Ready to change how you see the world? Get 12 principles for understanding the fabric of reality at realityprinciples.com. What do you think? Is humanity's confinement to the solar system a tragedy or a clarification? Tell me in the comments. If this changed how you think about the future of humanity and our relationship to the rest of the cosmos, if the physics of interstellar travel looks more like a definitive boundary than a temporary challenge after going through each of the layers, tell me in the comments. Tell me whether you find the energy argument, the biological argument, or the destination argument the most decisive. Tell me whether the conclusion that humanity's future is here in the solar system and not among the stars changes how you think about our responsibilities to this planet. And subscribe if you want to keep going into the places where the laws of physics set limits that are not just technical constraints, but statements about what kind of universe we actually inhabit